Hey guys, I want to do a quick review here and I want to review some equivalent statements. And these are going to be statements that we've seen for the past two chapters, for the past month of the course. And I want to remind you why they're true. So I'm going to write down all these equivalent statements, but I want to go deeper than that. I want you to know and remember why these things are equivalent. Because it's not good enough just to know that certain things are true and certain things imply other things. It's important to know why that is. And so I'm going to start with an m by n matrix, m rows, n columns, and these don't have to be the same number. And I want to start by thinking about solutions to systems of equations. So if I set up a matrix equation like this, of course this could be viewed as a system of equations. And I want to assume that this always has a solution. If I put any b over here, I always have a solution. Now, b is something in Rm. That's because I have m rows. And x is a vector in Rn, since I have n rows. So I want to come up with some statements that are equivalent to ax equals b having a solution for all b, for every single vector I put there. And the first one you might remember is just, it comes basically from the definition of what an onto transformation is. If I look at the linear transformation from Rn to Rm, with standard matrix A, then that transformation is onto. And if you look back to the definition of what an onto transformation is, this is pretty much the same statement. And if you don't remember what the definition of onto is, I urge you to go look at the video where onto and one-to-one transformations are introduced. I think it appears in section 1.9. So definitely take a look if you don't remember this, but this statement it pretty much follows quickly from the definition. So there's not too much to say here. Now, the next thing I could say has to do with pivots. And so if you have a solution for every single b, or if t is onto, there's something you could say about pivots. And I'm going to write down what it is, and then I want to explain why it's true. Because it's important to remember why these things are true. So these two statements are equivalent to A having a pivot in every row. So if you row reduce this matrix A and you see that you have a pivot in every single row, then you know automatically that this will always have a solution. You'll also know that the linear transformation is automatically onto. Now, why is that true? I do want to talk about why it's true. And the best way to think about this is, instead of thinking about what it means for this to always have a solution, think about what it means if this does not have a solution. If there is a b that I could put here and this does not have a solution, what does that mean about A? What does that mean about the augmented matrix? So if Ax equals b has no solution, think about what happens. I mean, you put A and B in an augmented matrix, you row reduce. If you have no solution, you have to end up with a row where you have a bunch of zeros and then something that's non-zero at the very end. So the row reduced echelon form of the augmented matrix that I build when I'm trying to solve this system has a row that looks like 0, 0, 0, all zeros, and then I have something that's not 0. So this is really an if and only if statement, and maybe I should write it that way. Ax equals b has no solution if and only if the reduced echelon form has a row that looks like this. So that means if I do have a solution for every single b, that means I should not have a row that looks like this at all. And if I'm never going to have a row that looks like this, since b could be anything, that means this b could also be anything. If I'm never going to have a row that looks like this, then there has to be something that's non-zero in these first entries. In other words, every single row of A has to have a non-zero entry in it. which is the same thing that A has a pivot in every single row. Pivot in every row of A. So that's why this is true. That's why you have this if and only if statement here. If you always have a solution, then you have to have a pivot in every row. Why? Well, because if you don't have a pivot in every row, you'll end up with something like this. You can find a B that you can put here and end up with a row that looks like this. And this row tells you have no solution. So there are a couple more statements I could throw in here and bring up the language of linear combinations and spans. So the next statement that's equivalent to everything else is that every B, every vector in Rm is a linear combo of the columns of A. And so let me explain why that's true. And I'll explain why it's true to this first statement up here. So if I always have a solution, I want to show that this is the same thing as saying that every B is a linear combo of the columns of A. And the equivalence here has to do with just remembering what A times X is, how to actually perform this multiplication. So let's say A looks like A1 to AN, those are the columns of A. X is the vector x1 to xn. So if I look at AX equals B, if I rewrite A times X, remember how you do that, or one way to do it at least, is to multiply each column by each entry in this vector and add them all up. So A times X, I can write it as x1 times A1 plus x2 times A2, all the way down the line. And when I write it this way, this is precisely the definition of a linear combination. I have that B is a linear combination of A1, A2, AN. It's a linear combination of the columns of A. So this is a linear combo of the columns of A. So if this equation has a solution, meaning there's an X here I can put to make this a true statement, that means this is a true statement. That means there are numbers I could put here such that this entire linear combination equals B. So this has a solution if and only if B is a linear combination of the columns of A. So now putting this together, if we say that this has a solution for every single B, that means that every single B is a linear combination of the columns of A. Now finally, we can think about this in terms of spans. I can say that the columns of A span Rm. So that means if I take the columns of A, so let me write it differently. Let me say the span of the columns of A. If I want to write it in a more mathy way, I can write it this way. So if I take the columns of A, A1 to AN, and I look at the span, this is all the linear combinations, I have to get all of Rm. All right, well, why is this true now? Why is this equivalent to all of these? Well, we can show that this is equivalent to this previous statement. And since we know this previous statement is equivalent to the first statement, which is equivalent to these two statements, that'll show that everything's equivalent to each other. So here, obviously the span of a bunch of vectors is inside of Rm. So the span is always like, inside of Rm. But we want to show the opposite. Like, is everything in Rm in the span of the columns of A? And the answer is yes. That's what this says. This tells me that every single vector in Rm is a linear combination of the columns of A. That means every single vector is in the span of the columns of A. So if every single vector in Rm is inside the span, that means these two sets have to be the same thing. They have to be equally to each other. So this statement is pretty much this statement. It's just wording it differently. But they are really saying the exact same thing. And so here are 5 statements that are all equivalent to each other. All right, so let's go back to this first statement here. Notice that I said at least one solution, so that of course means one or infinitely many solutions. Now, what if I have 0 solution? Let's think about sort of the opposite. This was at least one. Let's think about at most one. That's our next statement. At most one solution, that means 0 or 1. I want to come up with some equivalent statements to this. The first one has to do with linear transformations again. So if I look at the linear transformation with standard matrix A, I can say that it is 1-to-1. And once again, this is just the definition of 1-to-1. If you remember what the definition of a 1-to-1 transformation is, it just boils down to this when we have a linear transformation. It just boils down to this always having at most one solution, no matter what B I put here. So again, if you don't really remember that basic definition, go back to the 1-to-1 and onto video from 1.9 and refresh your memory with that. But let's do some other ones. The next one I want to think about is, I want to think about a special case of this equation. Let me put 0 over here, because I'm saying that this always has at most one solution. So let me think about the homogeneous equation AX equals 0. So we know AX equals 0 has one solution. It has the trivial one. I could always plug 0 into this, and it makes sense. So this has at least one solution. And usually you try to figure out if you have non-trivial solutions. But this is telling us now that this has at most one solution. So that means that this must only have the trivial solution. It has exactly one solution, and it's a trivial one. So this first statement implies that AX equals 0, the homogeneous system, has the trivial solution only. And we could also go backwards with this. If this only has the trivial solution, we can show that we end up that with this equation always has at most one solution. And to see that, so I guess we technically haven't shown that yet. So let me erase that. Let's say I've only done one direction. We'll see the other direction in a minute. Let me do an if and only if here. So AX equals 0 only has a trivial solution if and only if A has a pivot in every column. So I claim that these two statements are equivalent. So let me box this off from the rest for the moment. Put that in blue. So this statement is equivalent to this statement. Why is that? Well, think about this equation here. It only has one solution. That means A has no free variables. If A has no free variables, that means there's a pivot in every column. So AX equals 0, one solution. That's if and only if no free variables. That's if and only if pivot in every column. So that's why these two statements are equivalent. And now if you have a pivot in every column now for A, that implies that this equation, no matter what B is, this will always have at most one solution. If you have a pivot in every column of A, there are no free variables. No matter what you put here, you will never have a free variable in this system, no matter what B is. So you will always either have no solutions or one solution. You will not have infinitely many. So think about the logic there that we just went through. We showed that this is equivalent to this statement, and we showed that this statement implies this statement. So we just showed that AX equals 0 has only the trivial solution implies this first statement. So now we have the if and only if here as well. And I can get rid of this blue line now, but it's going to erase a bunch of things. Let me zoom in. Let me do something awkward in a video and zoom in. Erase this blue line so it's no longer in the middle of everything. I was trying to figure out good ways to incorporate the zoom function in my videos, but never really came up with one. I have to maybe in a future one, we'll see. Anyway, So we have this string of 4 if and only if statements now. These are all equivalent to each other. Now the last statement has to do with linear independence. And I can say that the columns of A are linearly independent. Columns of A are linearly independent. Okay, so why is this true? Why is this equivalent to everything else? Well, I'm going to show that this statement is equivalent to AX equals 0 only having the trivial solution. I'm going to show that these two are equivalent. And again, these two were shown to be equivalent already in the past. If you look at the video where we introduced linear independence, you'll see that this was actually shown. But I want to go through it again here. Again, this whole video is meant to be a review, and I'm just trying to piece together a lot of different equivalent statements and putting them all in one place. So to show that equivalence, let's see. If I want to say the columns of A are linearly independent, what does that mean? Well, it means if I set up an equation that looks like this, if I take a linear combination of the columns of A and I get the 0 vector, so if, then x1 to xn, all of these scalars, all of these real numbers in front of my vectors have to be 0. So in other words, this only has a trivial solution. That's what it means. That's the definition of linear independence, the basic definition. Now, if I look at the left-hand side here, I have this linear combination. This I can rewrite in a matrix equation. It's the same thing as saying A times X equals 0. And again, this is where A is the matrix whose columns are A1 to AN. X is a vector whose entries are X1 to XN. If you do that product, you end up getting this quantity, this linear combination. This is what we showed on the previous slide. Remember, we did the same exact computation here. So saying that these x's have to be 0 is the same thing as saying that this equation only has a trivial solution. Only has a trivial solution. So the columns of A being linearly independent is equivalent to saying AX equals 0 only has a trivial solution. And again, we already showed that AX equals 0 only having the trivial solution is equivalent to A having a pivot in every column, which is equivalent to AX equals B having at most one solution for all B, which is equivalent to this transformation being 1 to 1. So all 5 of these statements are equivalent to each other. One implies all the rest. Now it's also worth noting that the way I went through this and discussed why these things are equivalent, there are different ways to go about it. There are different ways to prove that these things are equivalent. So maybe you have different ways of seeing it, and that's great. But here I was just showing you one way to look at it. Now you might be thinking, like, you look at all these statements and maybe the invertible matrix theorem is fresh in your mind and you think, wait, these all appeared in the invertible matrix theorem. And, in the invertible matrix theorem, pretty much all of these statements are equivalent. All of these and all of these are equivalent to each other in the invertible matrix theorem. But here, well, in the invertible matrix theorem, you're dealing with an n by n matrix, so rows and columns are the same. What I've given you here is something more general, because I just have an m by n matrix, so the number of rows and columns are not the same in this setting. But if now I assume that n and m are the same, then all of a sudden everything becomes equivalent. So all 5 of these statements are still equivalent to each other, but they're also equivalent to all 5 of these statements. So that's the last thing I'll say here. If n equals m, so if A is an n by n matrix now, then all 10 statements are equivalent. Meaning you have like 10 if and only if statements you can throw in there. And this is pretty much just like the content of the invertible matrix theorem. So to see why those are all equivalent, I recommend go looking at that video again. And it's that video in itself is almost like a review video because it goes through all of these ideas and it mentions a lot of the same things I mentioned here, but it also has other things that it looks at because the invertible matrix theorem has a bunch more statements than are just listed here. But that's it. That was this little review. Again, this is not meant to be a comprehensive thing that reviews everything that you need to know for the exam, but here are just some random statements that I wanted to make sure you guys understood and you understand how to get from one to the other and why they're all actually equivalent. Because it's more important to understand why things are the way they are than to just memorize that two things are equivalent to each other.